This here, this algorithm for ST connectivity, is actually a very specific example of a more general idea known as depth-first search. So this idea of exploring your neighbor's entire subgraph before moving on to your next neighbor is known as depth-first traversal. So in this graph here, we think of, if we're starting from S, we explore one's entire subgraph before we use this edge 0, 3. That's very important. That's what depth-first search is all about. It's called depth-first because you go as deep as you possibly can. Now I should note that it is entirely possible that one subgraph also includes 3. Maybe there's a node or an edge that goes back up to 3. But this is still considered depth-first because we're not going to use the edge 0, 3 until one's entire subgraph is explored. This is made famous, I think, well, not that famous, but there's always a nice KCD for things. I'm not usually a, hey, look, here's a funny comic about stuff, but I think this one really drives it home in a way that's emotionally resonant. So you might imagine you have a date where you have many different problems you might run into. So you imagine different scenarios that could be a problem, and then you think, well, if there's an emergency, like a medical emergency, well, it could be that there's a snake bite, a lightning strike, you fall. Okay, well, you need to know what kind of snakes are dangerous, so you look up information about snakes, and then you spend a bunch of time building a spreadsheet, and then finally when your date arrives, all you can explain is the preparations you've been making about really dangerous snakes. And he goes on to say, I need to stop using depth-first searches. Okay, so in some cases, depth-first searches are really great, but not for date preparation. So let's see another example of how depth-first search can be useful. Let's suppose instead we don't just want to know does there exist a path from S to T, but we want an algorithm that computes a path to every single vertex. So it might seem daunting, like what would that even mean to find a path to every vertex? But we'll see that depth-first search, along with some handy instance variables, actually gives us a very natural solution. I will call this algorithm DepthFirstPaths, and when we run this algorithm, the basic idea is that it's going to be the same approach from before. It's just that now, instead of merely returning true or false if we find the thing we're looking for, we're going to maintain 2 instance variables. One is going to be an array of edges, and the other is going to be an array of marks. Okay? So I'm going to start by calling DFS of 0. Now, you might have imagined I would say DepthFirstPaths of 0, but I'm going to imagine that my DepthFirstPaths algorithm has a helper method called DFS. Okay, so DFS is a helper method that's going to do these things. So the first DFS call is on 0. We say, I'd like to search the space starting at 0. So DFS says, sure. So the first thing I'm going to do is mark 0. We set this value to true. And then for every unmarked adjacent vertex, W, we're going to set the edge to of W equal to V. So this basically says, how do you get to 1? Well, you get there via 0. And now what we'll do is that since we have marked this with a 0, we're going to call DFS on it. Okay, so DFS1 is the next call. Okay. So we make the call DFS of 1, and I'm making a note of the ordering of our DFS calls for reasons that will become clear soon. So next up, we go to 1, and we mark it. And then for each of its unmarked adjacent vertices, so 0 is already marked, so we're not going to do anything with it. But since 2 is not marked, we are going to say the edge to 2 is equal to 1. That's just what it says to do. At that point, I will now call DFS of 2. And once I do so, we look back at 1 and we say, 1 is already marked. But 5 is unmarked. So I'm going to set the edge to of 5 to 2. Now let's reflect on what this edge to array is doing for us. It's actually a pretty clever idea. So you ask yourself, how do you get to 5? Well, you get there from 2. Well, how do you get to 2? You get there from 1. How do you get to 1? You just get there from 0. And so there, we've stored a path implicitly from 0 to 5 through each of these edge 2 links. I think it's pretty cute. Okay, so next we call DFS of 5. 5 will look back at 2 and say, hey, 2, I'd like to check if you're marked. And 2 says, yeah, I'm marked. Look, the value is true. However, 4 is unmarked. So we're going to set 4's edge 2 value to 5 and then call DFS of 4. So in this case, every time we're visiting a node, we're thinking about that as meaning setting its edge. So now we traverse 4, and at this point, we say 1, you're already marked. 1 is already marked, but 3 is not marked. So since this is unmarked, we're going to set its edge value equal to 4. Okay? And we're marking ourselves. Wait a sec. 4. Oh, sorry. Yeah, and we're marking ourselves. I got a little confused for a minute. The first step is to mark yourself. All right, good. Okay, so at this point, since 3 is not marked, we're going to go up there and call DFS. And at this point, DFS, once we get to 3, so we mark 3, and then since 4 is already marked, we're just going to return. Now, there's no return value. We're just done. And at this point, I'm making a note that 3 is finished. So this is the first DFS call, the first recursive method call that is finished. Same as before, right? The first connected call that finished was 3. Same deal here. The first DFS call is also 3. So we get back up to 4, and 4 has no more unmarked children, so we go back to 5. Okay, so how about 5? Well, we've already checked 2 and 4, so now we need to check, is 6 marked? Well, it is not marked, so we'll set its edge 2 value, called DFS. At this point, we say, is 5 marked? Yes. Is 7 marked? No. So we will set its edge 2 value, and then we will call DFS on it. Okay. So now that we have completed this process, at 7, we return from 7 and come back up to 6. 6 is now done, so we return. We're at 5. So now we look at its last remaining child, which is 8. It is not marked, so we set its edge 2 value. Then we call DFS on it. Then we go back up. We're done with 8, we're done with 5, we're done with 2, we're done with 1, we're done with 0. And so these are the orders of the calls we made to DFS. These are the orders in which we return, and that'll be something interesting soon. But really the more important thing is this algorithm has produced for us an artifact. It's given us a path to every single node. So for example, how do you get to 7? You get there from 6. How do you get to 6? You get there from 5. How do you get to 5? You get there from 2. How do you get to 2? You get there from 1. How do you get from 1? You get there from the source. So DepthFirstPaths gives us a correct algorithm for computing the distance, computing a path. It is a correct algorithm for computing a path to every vertex.